the stage to the second speaker of this session, who is Ludovica. CICCI, I can hear you. Ludovica, you can share your screen.
Yes. Okay, can you see my screen now?
Yes, perfect.
Okay, and can you hear me well?
Yeah, absolutely. So Ludovica is PhD student within the higher project in Milano at MOX, in the Department of Mathematics. And she's going to talk about a deep learning-based operator approximation for modular order reduction in cardiac mechanics. So please, Ludovica, the floor is yours.
Thank you. So hello, everyone, and good afternoon. I am, as I said, Ludovica CICCI, PhD student from the Politecnico di Milano. And I will introduce our novel method to perform mode order reduction of nonlinear time-dependent parameterized problems by relying on a deep learning-based operator approximation with a particular application of cardiac mechanics. This work is part of the High Art project and has been conducted in collaboration with Stefania Fresca, Andrea Manzoni, and Alfio Quarteroni. So first of all, let me give you a brief introduction of what are the motivations to perform mode order reduction, although I assume many of you are already well aware of them. So cardiac mechanics model governed by a partial differential equation, which is nonlinear and time-dependent. That is the equation of motion for a continuous medium from within the reference configuration. Furthermore, we have to include boundary initial conditions and suitable constitutive law describing the material behavior, such as the Guccione or the Oxaffe-Ogden one that feature exponential nonlinearity. All these components of the initial boundary value problem depend on a great set of coefficients and parameters that have an impact on the solution of the problem under investigation and on outputs on clinical interest, such as, for example, the pressure volume loop or other quantities associated with it, like stroke volume, ejection function, to name a few. And therefore must be suitable chosen to develop patient-specific models. Moreover, in many applications, we are interested in inferring about unknown or uncertain parameters from available data or measurements of these outputs of interests, which depend on the solution to the PDE, or in assessing how uncertainty in the inputs affect the solution of the problem under investigation. In this multiple context, but also for the model to be used in clinical practice, using an expensive high-fidelity approximation of the underlying differential problem is unfeasible from a computational standpoint, as each evaluation of the input-output map may require hours or even days of computations. And for this reason, the development of efficient but still accurate reduced order models is of paramount importance. So, as I said, we are interested in the solution of a parameterized initial boundary value problem with the following nonlinear time-dependent PDE, where the input parameter that I denoted with the Greek letter mu may represent the coefficients of the constitutive relation, fiber orientation, material properties, boundary initial conditions, and so on. The associated high fidelity full order model, which I refer to as the FOM, may be obtained, for example, using the finite element method for the space approximation and the backward differentiation formula for time discretization, and may be seen as a sequence of NH-dimensional nonlinear algebraic systems whose solution entails huge computational costs as soon as the dimension NH becomes too large. And this dimension depends on the mesh size and on the underlying discretization scheme. So reduced order models featuring smaller dimension and lower complexity have been extensively developed to overcome this computational bottleneck associated with the FOM. So in this work, we construct a projection-based ROM, reduced order model, by relying on the so-called reduced basis method. The key idea is to approximate the FOM solution by a linear combination of few problem-dependent basis functions, which are built by performing proper orthogonal decomposition on high-fidelity solution snapshots. And the ROM is then obtained by forcing the FOM residual evaluated on the reduced solution to be orthogonal to this n-dimensional subspace spanned by this basis function, such that the reduced system has dimension n, which is much smaller than the FOM dimension nh. I would denote, I denote with the letter B the reduced spaces whose columns span the reduced solution subspace. However, due to nonlinearity, we need to assemble the high-dimensional arrays before projecting them onto the reduced subspace, undermining the ROM efficiency. For this reason, we need to find an approximation of the nonlinear terms that is independent of the high-fidelity dimension. The discrete empirical interpolation method represents a standard technique to perform system approximation, also known as hyperreduction. Nonetheless, when applied in the context of nonlinear elastodynamic problems, such as cardiac mechanics, it still suffers from computational burden, as it depends on the assembling of the nonlinear quantities onto a reduced mesh that is a subset of the original one, which, however, may still have a high number of nodes. Here, we propose the novel deep IROM-net method, which stands for Deep Hyper-Reduced Automodel Network, with the aim of replacing them for the hyperreduction stage, hence the assemble of the reduced system. In fact, for the application we have in mind, we have noticed that the computational bottleneck is the assembling of the nonlinear quantities onto the mesh grid auto-reduced rather than the POD dimension, and which can be kept sufficiently small. So Deep IROM-net is a physics-based reduced order model, still relying on the POD Galerkin strategy by employing a deep neural network architecture to approximate the reduced residual vectors and Jacobian matrices. In particular, given the triplets made of the input parameter mu, the current time step, and the Newton iteration, we are able to compute in milliseconds the corresponding n-dimensional ROM operators, and thus recover the efficiency online of the reduced model for the solution of the nonlinear system. The neural network architecture exploited in this work is based on the one developed by Stefania and reported in her article. And if you're interested, I invite you to follow the presentation tomorrow, I believe in room 3 again. So this procedure, the IROM-net, allows to guarantee an efficient decomposition into a costly offline phase, which is, however, performed once and for all, and an efficient online phase during which the problem solution is computed for a specific input vector. So first of all, during the offline stage, we need to collect form solution snapshots in order to construct the reduced spaces V. Then run ROM simulation to collect reduced nonlinear data, and finally train the neural network on this data. While during the while online, for each new instance of the input parameter, we evaluate the output of the neural networks in order to assemble the reduced system and efficiently solve the reduced problem. So in order to test the deep IROM-net method for the solution of cardiac mechanics problem, we started by considering the simplified problem of an idealized contraction and relaxation of a patient-specific left ventricle geometry, whose computational grid is shown here in the slide. And when blood and active tension are described by suitable analytical function extracted from electromechanical simulation, and which corresponds to the red and blue curve respectively. In particular, we made the active tension depending on a parameter, A tilde, that controls its maximum and that we assume to vary in a suitable range of values. So for the case at end, we use a coarse hexahedral mesh and linear filing elements such that we end up with a form dimension equals to almost 19,000, while only 16 reduced spaces are needed for the construction of the low fidelity solution subspace. Despite the computed pressure volume loops are not physiological, the aim of this numerical test is to assess the ability of deep IROM-net to accurately approximate the myocardial displacement during a cardiac cycle. Moreover, we proved that our novel method is able to solve the time-dependent problem much faster than the POD-DAME approach, as it requires less than a second to compute to solve the time-dependent problem, and for the whole cardiac simulation, whole cardiac cycle, still achieving the same results in terms of accuracy. The picture reported here in the slide show the comparison between the FOM and the deep IROM-net approximation for two different values of the input parameter, which was unseen during the offline stage. As a second test, we are interested in the solution of the coupled 3D, 0D structure in cluster model using, again, time-dependent parameterized active tension that surrogates the input provided by the active force generation model. So our model consists of the green and blue boxes, which mutually exchange pressure and volume, plus the surrogate input coming from the orange box. So for what concerns tissue mechanics, we are considering the Guccione constitutive law for the myocardium using a nearly incompressible formulation and rely on the active stress approach such that the first Viola-Kirchhoff stress tensor is given by the sum of the passive and active terms. The articulation instead consists of four phases, starting with systole. First, the pressure inside the ventricle grows from the end diastolic pressure to the aortic valve opening pressure, while the volume is kept constant, such that we have an isovolumetric contraction. Then the ejection phase starts, and the evolution of pressure is governed by a two-element Pincastle model. Then when the aortic valve closes, the pressure within the ventricle drops until it reaches the mitral valve opening pressure, where the volume remains constant, and this is the isovolumetric relaxation phase. And finally, the ventricle begins to fill again, such that the pressure linearly increases to the end diastolic pressure, concluding the cardiac cycle. In this case, during the isochoric phases, we have to deal with a saddle point system, such that we rely on neural network approximation for both the structural and pressure residuals and the associated Jacobians. So we consider the same pieces-specific geometry and spatial discretization of the previous test case, while we increase the number of time steps and the number of input parameters. That in this case are the bulk modulus appearing in the passive material law, the resistance of the Pincastle model, and the active tension parameter A tilde. And these parameters represent for the case at hand the most influential parameters, meaning that they have the greater impact on the computer deformation. By doing so, we need a POD dimension of 6 distributive bases in order to properly capture the system behavior. So in this case, the most efficient POD DAME reduced model that we obtain has a negligible speed up of 1.3 with respect to the form, while the IronNet is able to compute the PD solution in only 19 seconds. That is 160 times faster than the almost 37 minutes required by the phone. Still achieving good results in terms of accuracy, as shown by the myocardial displacement reported in the slide for two different parameter values. And this is the screenshot taken at the end systolic time instance. And also, as we can see by the computer pressures and volumes reported here on the right, where the solid line refers to the phone and the dashed dotted line refer to the deep IronNet approximation. Again, we have on the top the solution for the two different parameters, and on the top, sorry, the evolution of pressure, and the middle, the evolution of volume, and the bottom, the pressure volume loop. We point out that only 50 ROM simulations were run offline in order to collect the data necessary for training the neural networks. So to conclude, our next step will be the integration of deep IronNet in an inverse uncertainty quantification scenario in order to address the solution of clinically relevant parameter estimation problems. And furthermore, we would like to perform model order reduction for the solution of pathological cases, focusing on cardiac ischemia, that is the reduction of blood supply to the myocardium that may lead to the death of cells in the affected portion of tissue and therefore causing inhibited contractility of the myocardium itself. So thank you very much for your attention.
Thanks, Ludovica, for your presentation. The stage is now open for questions. The floor is open for questions. Comments or remarks, or raise your hands or unmute yourself and go ahead if you have questions or comments. I can start maybe asking you, Ludovica, if you can maybe point out a bit more, which is the computational complexity of, say, the deep learning based procedure you have proposed. So regarding both the speed up, but also, I mean, the offline stage, that in any case must be.
Yeah. So I just want to point out that the offline stage is not much different from the one required for the construction of the time reduced model, since we also, when we perform discrete integration method, we have to collect RAM solution for the construction of the basis associated with the residual. Offline, there's also the cost of training the neural network, but it's not, at least for the test cases we perform, is not, it requires only a few hours, while online is a very, very gain in computational time, especially in this case, but also in the whole cardiac cycle, where the pressure volume loop computer is much more physiological, since we do not need to, as I said, assemble the reduced vectors onto a computational mesh, but the neural network is able to compute each instance, each output of the network, which is the reduced residual order use Jacobian, in order of milliseconds. So this is the very huge computational speed up with respect to the time approach. So
Okay.
Okay.
Thanks. Is there any other comment or question for Ludovica? Well, if not, thanks again for keeping your
I just have to
time.
stop sharing now.